Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Sascha Trippe. He received his PhD, or better the German equivalent Dr. Nat, from the Ludwig-Maximilians University in Munich in 2008. And since 2011, he is now a professor at Seoul National University, first assistant and associate and now full professor. Thank you, Sascha, for agreeing to give this talk. The stage is yours.
Thank you very much, and thanks a lot, Torben, and the entire team for inviting me to give this presentation. So essentially, what I'm going to talk about is a project that we have been proposing in various iterations of the design. So for now, starting round about 3 years. And today I'm going to present you the latest iterations or the latest versions of this project that we have in mind. So essentially, the idea is the following. Wait a second. Yes, now it should work. Yes. You may all be familiar with some of the recent, let's say, spectacular observations of the shadows or photon rings around supermassive black holes in M87 and in the center of our Milky Way, Sagittarius A star. And so essentially, one way to represent this kind of this kind of approach to the observations is using this kind of collage of collections of radio maps of M87. So where essentially on the left hand side, you see with a specific observatory at very low frequencies, 50 megahertz, very low radio frequencies. So you see essentially the distribution of the gas throughout the entire galaxy, and then using more and more elaborate radio interferometric arrays, observing at higher and higher frequencies. So you can stepwise, you can zoom in into the central engine of this active galaxy. So first you actually you start to see a pronounced jet and lobe structure, typical for radio AGN. Zooming in farther, so you start to see the foot point of the jet, so the radio core, the jet itself, as well as hints of the counterjet. Well, due to relativistic beaming, so we usually see only one of the two jets, but this is supposed to be a symmetric bipolar structure. And last but not least, using pretty much the highest frequencies, where we can do this kind of observations from Earth, and going to actually to a global array. We have the Event Horizon Telescope that was able to observe the shadow and the light rings around the shadows of M87 stars, the supermassive black hole, and from the diameter of this shadow or this ring, and the assumptions that general relativity applies, which is usually a very good assumption. Then we know that this supermassive black hole has a mass of around about 6 billion times the mass of the Sun, which is indeed pretty much at the upper end of the distribution of black hole masses as we know it. This was specifically for two sources, M87 and our own Milky Way. And we could only do this because these are by far the largest sources on the sky in terms of angular diameter. So essentially, for M87 and Sagittarius A star, so the angular diameter on the sky is about 40 to 50 microarc seconds. This is a very small number. But as it turned out, with a lot of effort, long-term preparation, it was just about doable. To build, the EHT with an angular resolution of about 20 microarc seconds, to resolve and to obtain images of these two, or the shadows of these two black holes. This is, of course, the existence of such a shadow is a fundamental prediction of general relativity. Specifically of the Kerr metric. So you expect actually a shadow which is about 5.5 times with a diameter, which is about 5.5 times the diameter of the actual black hole, at least the Schwarzschild in terms of a Schwarzschild black hole. But as well, this is still a very small structure or very small feature. And these two sources that we observe with the EHT, that's all we can do with ground-based observatories. So now, on the other hand, what we can do is we can actually look at at the population of supermassive black holes, so of which we are aware, well, there are two parameters to be considered. So one parameter, this is the horizontal axis in this case, is the angular diameter on the sky. So if this black hole shadow should be large enough to be actually observable by your observatory of choice. And on the vertical axis, we have, well, the luminosity, so or the brightness of the central engines, so of the materials right around the black hole, of the ring itself, ideally, because of course only if that feature is bright enough we will actually be able to observe it, regardless of the size of the black hole. So if we consider this, so both the sizes as well as so the visibility in terms of sensitivity limits. So wherever you do the cutoffs, so around about 10 additional supermassive black holes in other galaxies should be observable if you're able to design an instrument, an observatory, with angular resolutions, so somewhat below 10 microarc seconds, so maybe 2, 3, 4 times better than the Event Horizon Telescope. Well, one thing, as it turns out, this can only be done with radio observatories, so as we know. And so if you do it at radio frequencies, so you have to go to the high radio frequencies, so higher than 200, at least 200 gigahertz. Otherwise, for the lower radio frequencies, so the material, the interstellar gas around the black hole might be optically thick, so you might actually never be able to look all the way down into the immediate environment of the central black hole. So. Well, of course, so observing these black hole rings and black hole shadows, and this way essentially confirming or finding a good agreement with, that's how I should phrase it, finding good agreement with the general relativity and with the predictions made by the Kerr metric. So of course caused a lot of excitement, so in terms of fundamental physics. But of course also it raises a lot of additional astrophysical questions. So now, once we're actually able to see down all the way, or almost all the way down to the black hole, we should, as it turned out, we should have seen more, especially in case of M87. So in M87, we have, as we see in the bottom left, so we have theoretical images, so that would look somewhat like this. We have the actual observation of the central, the centermost region around the black hole. And essentially, so as it happened in the observations, so we only saw the light ring, with the black hole shadow itself. We did not actually see so the foot point or the starting regions of the jet, which is there. I mean, we see it in multiple other radio observations, and even at visible light observations, even if at larger angular scales. I mean, on the right-hand side is another recent, relatively recent, actually more recent than the Event Horizon Telescope observation, so recent radio observation of the environment of the M87 black hole at a somewhat lower frequency, so which means we are not looking all the way down onto the into the black hole shadow. So, but we do see the outflow starting from the environment of the black hole. So we know the jet is really going all the way to the immediate environment of the black hole within tens of Schwarzschild radii. So, but we could never see this, we could not see this in the Event Horizon Telescope or similar observations. Well, probably because of spatial filtering. An interferometer acts as a spatial filter. And well, essentially, as it happens, I mean, in an interferometer, at any given time, so any pair of antennas measures one point of the 2D Fourier transform of the target image, roughly speaking. Well, and if you don't have a lot of those data points available, so the target image will be highly incomplete and will miss flux or structures at certain angular scales. And this seems to have been the case here for the jet itself. So if in the future we want to actually understand the astrophysics of AGN jets starting from the immediate environments of black holes, so as they do, as far as we know, so then we would need to have the ability to have high quality images. So we would need an interferometer, but an interferometer which is able to provide a complete or almost complete map of the image without missing actually major parts. Another science topic so that has kept the community, well, I'm from the black hole and AGN community. This is why I get so excited about this so easily. So, but another science topic that has kept us busy actually, or has kept us thinking for a long time is also, there are certain sources, certain AGN, for which it looks like as if we are not looking at one supermassive black hole, but at a binary of supermassive black holes. A supermassive black hole binary, a closed supermassive black hole binaries. So we are talking about orbital timescales of maybe a few years to maybe a few thousand years in the most extreme cases. So the most famous case is this object, OJ287, where there have been very detailed proposals so suggesting that we have a very massive primary black hole, so 18 billion solar masses, which is, essentially, which is orbited by a much less massive, but still supermassive black hole with about 150 million solar masses so the center of mass of the system is pretty much the primary black hole. So that on a 12-year orbit. And then, essentially, so because this is a periodic motion, so periodically, so the secondary black hole will penetrate the accretion disk of the primary and cause all kinds of phenomena that, for example, outbursts of radiation, maybe so modifications of the jet from the primary black hole, which is clearly there. And the periodicity of those phenomena also gave then rise to this 12-year binary black hole model. But there are other possibilities, other physical possibilities. So a supermassive binary black hole is usually not the only possible explanation, neither for OJ287 nor for other sources so that have been over the years proposed in the literature. And again, actually looking into kind of systematically looking into the population, surveying the population of supermassive black holes in the local universe. So at least in theory, we would expect something like around about 20 supermassive binary black holes within redshift 0.5 with a proper motion, so more than about 1 microarc second per year. So which should be available for observations with future observatories like the ones which I'm going to discuss here soon. And indeed, but if we want to actually solve the puzzle, are we really looking at a binary black hole here or maybe at something else? So we need, multiple observations, because there may be two objects or two active nuclei moving relative to each other, maybe. And we need actually a very good image quality, so a very good visibility plane, Fourier plane coverage, so for interferometric observations, because we need a complete 2D picture of what's happening actually in this system. As I will actually show in a few minutes, so when you have a radio interferometer of the kind so that we are working with already, we are talking always about VLBI, so very long baseline interferometry. So very large distances. So it turns out you need actually the light or you need the light source you observe to be highly concentrated. So the critical parameter is the brightness temperature, which is one way in the radio community to essentially express the the brightness per unit angular area. Or per angular area so in the sky. So as it turns out, so when you look at this or when you compute this brightness temperature, so this is much larger so than any thermodynamic, usually much larger so than any thermodynamic temperature so you would expect from any, let's say, a black body emitter. So this means that for VLBI observations, thermal emitters are usually not observable. But we can actually kind of turn this around and use non-thermal emitters like AGN jets, which are strong emitters, which are emitters of strong synchrotron radiation. We can use AGN jets as background sources that illuminate, for example, the material around them, the interstellar gas around them. And this is what actually happens so in this kind of observations. So essentially where this group used the KVN, the Korean VLBI network, to look for molecular absorption lines in the jet or in the image of the jet, of a specific AGN, in this case NGC 1052, a famous source in the community. And they found with, of course, integrating data for a sufficiently long time, so they indeed found some absorption lines of molecular gas, which surrounds the jet and the central engine of the AGN. So, well, once we actually have those absorption lines, so we can place constraints on, well, the kinematics, of course, Doppler shift and broadening. We can also place kinematics, we can place constraints on how abundant certain molecules are indeed actually in the interstellar gas, which is secreted toward the black hole. So this is something that has been done essentially only once properly, which is this observation shown here. But if we are able to actually zoom much farther inward, look into a large sample of AGN at large distances, where we would need to observe at much smaller angular scale, so we would be able to systematically search for indeed signatures of the molecular gas around or within around the central engines and within the accretion zones of those active galaxies. But again, this would require very good angular resolution and the ability to construct high quality images of the target region. Well, there are quite a few other science cases which have been discussed in this context. Some of them are more exotic than others. One example, which I came across a few years, which we've discussed a few years ago, was this one. NGC 1068 is a nearby active galaxy, but about 14 megaparsecs away. That's local universe. But this source is also the source of neutrinos. So we know that NGC 1068 emits neutrinos, at least one, probably a few by now, which immediately raises the question, which processes actually create those neutrinos where in the AGN? And well, I guess there are, at least that was my understanding from the discussion a few years ago, there are at least as many theories as there are people working with this source. But this is just what I'm bringing up here. It's just one specific example, which I liked because this group made a very specific prediction about where to look for. So actually, the emission that could provide hints, actually radio emission, that could provide hints at where the neutrinos that we observe on Earth are actually created. In this case, the idea was that essentially, there's an AGN with an accretion disk around the central supermassive black hole. And this accretion disk, above and below the accretion disk, you have a so-called corona, so material which is much hotter than the accretion disk itself, which is a prominent emitter of high energy radiation, but also would be visible at all the way down to sub-millimeter wavelengths, so high frequency radio observations. So if we were able, in this specific scenario, if we were able to constrain such an amount of emissions, so in a very small area, in this case within 30 Schwarzschild radii or a few micro arc seconds from Earth, so then this would lend credibility to this kind of corona emission scenarios, so for the neutrino emission from NGC 1068. But again, of course, this requires angular resolutions of better than 10 microarc seconds, because you need to be able to pinpoint the position of a point source, so within 1 or 2 microarc seconds. Okay, well, so far I've only talked about supermassive black holes, and well, it turns out of most of the scenarios, for which such an observatory, as I'm going to discuss here today, is of interest, so indeed involve active galactic nuclei, the one way or the other. But that's just for completeness. I want to point out this is by far not everything. I mean, as I mentioned before, VLBI is usually not able to observe thermal radiation or black body radiation from a target. But which means stars or stellar sources are usually out of the question. So unless you have stellar activity, which is highly non-thermal, which emits highly non-thermal radiation. For example, as we have here on the left-hand side, so a cataclysmic event. So this is RS Ophiuchi. So it's a famous cataclysmic binary. So that underwent a nova outburst in 2021, and as it turned out, so this nova outburst, so essentially where we assume so that material is streaming from a main sequence star or a giant star onto a compact remnant, like a neutron star or a white dwarf. So then at the surface or near the surface of this compact remnant, so you will have an outburst of radiation, an outburst of a cataclysmic release of energy. This can create emission, which is highly non-thermal. This process also can create radio jets. So this is actually what people here in the case of RS Ophiuchi actually found. So that about once they observed this with the European VLBI network about a month after the outburst, so they found a clear hint so that both from the central source, both to the west as well as to the east of this central event of this energy outburst, so radio emission, so hot gas, hot gas. Well, if it's synchrotron radiation, it would be magnetized gas, magnetized plasma, was released and could be observed. On the right-hand side, this is actually an observation that was completely coincidental, and this kind of observations is exceedingly rare. So this is why I bring here an example map. So again, a VLBI map. Well, actually VLBA, Very Long Baseline Array in New Mexico in the US, of a VLBA map that was obtained more than 20 years ago, because there are very few actually of such maps. Essentially what happened is, so this group was looking for something else or was observing something else, and just by chance within the field of view of their observations, so suddenly another light source erupted. And it turned out later, the observations were pointed toward Orion KL, so the star forming region, famous star forming region. And it turned out, so at the location of this sudden unexpected outburst, there is a young stellar object. So, we know that some of them have strong magnetic fields, and we know that some of them can flare, so can create jets actually, and they can actually flare, so can emit non-thermal radiation. And in this case, and that was then the unexpected part here, so it was really a strong radio flare, so that could be observed long enough to actually create a very significant signal, even if it's basically just a point source. So in these interferometric observations. So one thing so we can look at is, okay, let's say we look at distances to some of, let's say, interesting regions, for example, nearby star forming regions like Orion KL, which is about 400 parsecs away. So then at such a distance, so the diameter of the sun has an angular size of 23 microarc seconds. So if you're able to build an observatory which can observe at scale smaller than that, we might not only be able to pinpoint this kind of events more precisely, we might actually be able to tell where it exactly comes from. Does it happen at the stellar surface or actually away from the star somewhere in the circumstellar medium, or in a jet of a young stellar object, or whatever we can imagine? So that's an exciting possibility for the stellar physics community, if we can do it. Okay, so essentially, I could go on a bit longer, but that would take too much time. Sorry for that. So essentially, the idea that we have is, okay, there are various science cases that can only or that requires that can only be handled if we have micro arc second scale resolution, which is a very small scale on the sky. And only radio interferometry can do that. VLBI, so very long baseline radio interferometry with observatories separate by thousands of kilometers. So tens of thousands of kilometers. We need good image quality, which means we do not only need to have a very good resolution and a few data points in the visibility plane, but we need to obtain as good as possible, as far as we can, the full 2D Fourier transforms of the target on the sky. Because only then we have sufficient image quality, image fidelity. And at least for some of the sources, so we need to go to high frequencies because we need to peer through interstellar matter, which is, well, intransparent at lower frequencies. So we need to go to high frequencies at which the atmosphere of Earth is opaque, so at frequencies higher than round about 400 gigahertz. So the conclusions so that we came up with, well, not we, of course. So there's a long list of works that had similar ideas long ago, or not that long ago, but a while ago. So the conclusion that then emerges is, okay, let's go to space by placing a few satellites in low Earth orbit. So that's our design. That's what we call the Capella program, Project Capella or Capella program. I will make the distinction clear in a moment. So each satellite essentially has a full VLBI station, a full radio observatory with all the equipment needed to actually, well, not only to receive the signals from the sky, but to actually record them and process them as far as needed. So we need a radio telescope on board, receivers, digitizers, recorders, and so we need a frequency reference systems, and so navigation, etc., and fast communication from the satellite to the ground. And so the idea is then, okay, we have this network of satellites, so up to 4 satellites is what we have in mind in space. So then these satellites send their data to the ground, and on the ground, so we correlate the data in a dedicated computer center, so in the correlation center. Well, this correlation then constructs actually so the image of the target. Okay, so, well, for the actual science observatory, is what we call Capella. So the idea was to have 4 identical satellites in, well, essentially in 4 separate orbits, but low Earth orbits, but in 2 perpendicular planes, polar planes in this case. Which makes things a bit easier in terms of, for example, planning, so launching those satellites, because 2 satellites can share, right? If they go to the same orbit plane. So, and well, it's 4 satellites. So when we thought about a name for this project, so well, we came up with, okay, Capella. It's a famous quadruple star. We have 4 satellites, and so this is why we called this observatory Capella or Project Capella. So, and the point is now that in the last few years, so technology has evolved a lot, and now, and actually only now, so only for the last few years or so, technology has been far enough, so has evolved far enough so that we can actually fit an entire functional radio observatory with all the specifications that we need into small satellites. So which kind of, well, small usually means less than round about 500 kilograms, so which is nowadays kind of a standard platform size, so that's, well, almost mass production size if you think about Starlink or other future internet communication constellations. So we tentatively pick a certain set of orbits. So we picked a frequency band at 690 gigahertz, so which is essentially inaccessible from the ground, not completely. There are 2 or 3 stations on the ground, observatories on the ground, that can use this frequency band occasionally, especially ALMA, so in the Atacama Desert. So it's a scientifically interesting frequency band, and it's a frequency band where we know how to build the receivers and how to observe there. So that's why it's a good choice. So we have a certain instantaneous bandwidth. So the bandwidth of the receiver kind of tells us something about the sensitivity. So the wider the band, the more light we can actually receive and process. So that is good for the sensitivity. But if the bandwidth is too wide, so then we have problems with the data rate of the data that we actually need to send to the ground. So we have to balance everything, and 4 gigahertz seems to be a good choice currently. Well, essentially, so we have a few estimates. So if we assume kind of 3 square meters, a 2-meter diameter aperture, so 3 square meters geometric collecting area, 80% optical efficiency, so telescope plus receiving optics. So we have an effective aperture of about 2.4 square meters. And well, the great thing is, of course, once we are in space, so we can essentially keep staring at sources, so as long as we want. I mean, that's what of course the X-ray community has been doing for decades. Essentially, when you talk to X-ray astronomers, so they count observing times in units of megaseconds sometimes. So which means we're talking about sometimes weeks of observing time. Well, you can do that, of course, because you're not affected by atmosphere or Earth rotation as you are on the ground. So, well, you are affected by the orbit of the satellites. So your satellite will occasionally be shadowed by Earth. So you will have interruptions, but you could just keep pointing your satellites at your targets so as long as you want. So we assume that kind of the standard observing sequence will take about 250,000 seconds, or about 3 days. So which then gives us a certain estimates for sensitivities, so in units of Janskis, depending on if you need the final point source sensitivity in an image or in instantaneous sensitivity within a few minutes that you would need to for calibration purposes. Okay, so how does this actually work, what we are planning to do here? So I mean, what we are going to do is we are going to do VLBI, so very long base interferometry in space. So, and I mean, what such an interferometer does essentially is you have an array of telescopes. I mean, we plan with up to 4, but let's say 3 for illustration. And so each of these telescopes or each of these stations essentially collects the light from a target, so stores the raw signal, sends the raw signal to the ground, and on the ground it's correlated. So what happens then is, so this correlation is equivalent to, you can prove this mathematically, so this correlation is equivalent to creating an interference, so between the 2 light rays from the 2 telescopes. So what you get is, so then when you have interference, you have an interference pattern, so which has an amplitude and a phase, so which is a complex number. So this is what we call the complex visibility. And well, if you have 3 antennas, or 3 telescopes, you have 3 baselines, so 3 independent pairs. So you get 3 visibility measurements so at any given time. So when you have 4 telescopes, you have up to 6 baselines, 6 independent measurements for each time, for each point in time. So then, okay, so what happens is then, very conveniently, so there is, well, first of all, what we are doing is, so we are measuring, so essentially we are measuring a structure as it is here illustrated on the right-hand side. So we are measuring a so-called UV plane distribution. So visibility as function of coordinates u and v, and these coordinates u and v are basically just the pairwise distance of the 2 antennas. So in east, west, north, south. So it's a position vector. So in units of the wavelength. So it's a dimensionless, it's a coordinate. And so if you have enough data points, so enough observe long enough, and have enough separate different configurations, so different geometries of baselines and baseline orientations, so on the sky, then you can fill this UV plane more or less completely with data. So with ground-based VLBI, usually this is very incomplete, but in space, actually things become much easier so if we do it. And essentially, as we know from the van Sitter-Zennike theory, is that this UV plane distribution, so the distribution of the visibilities as function of coordinates u and v, this is the Fourier transform of the actual image of the target on the sky. So if we have enough data to fill this plane sufficiently with data, UV plane sufficiently with data, we take the Fourier transforms so we get an image of the target. So with an angular resolution that corresponds, or that is given by the maximum separation between 2 telescopes. lambda over d. So this minimum angle is round about a lambda over d wavelength divided by a maximum extension or maximum pairwise distance between satellites or between antennas. Okay, okay, I'm not going to go into great detail here, but this is an example using actual data of what is happening here. Essentially, we assume we have an image or a certain image of our target on the sky. So then, if this is the case, so then the corresponding UV plane distributions would look something like this. And this is actually what we measure. So ideally, we would measure this distribution, take the inverse Fourier transform, and get a map of the target. Well, of course, that's usually not exactly what's happening, because we never completely, infinitely well sample this visibility plane. But, well, we have a certain number of individual observatories, so with a certain number of baselines. So of course these baselines, well, either on the ground, Earth is rotating, so these baselines actually, they change orientation as projected on the sky, as seen from the point of view of the target. Or in space, of course, so you have rapid orbital motions of all the antennas. So you have some kind of sampling function, and what you actually observe, what you actually measure, is the product of the sampling function and the actual interferometric visibility. You get the inverse Fourier transform of that one, and you get a somewhat distorted, blurry image of your target, which then you need to still filter, process well enough to actually identify a sufficiently good map of your target. Okay, so we want to go to space. And as it turns out, of course, space VLBI has a pretty long history, and probably as a future, but with a twist. So essentially in the past, and even with existing projects right now, space VLBI always meant there's one antenna in space that was already with the TDRSS experiment in the 1980s with a communication satellite, and several antennas on the ground, and all of those antennas together observe the same target. This is, of course, until now or until very recently, this was pretty much the best that you could do. There are some, well, there only have been two dedicated space VLBI missions at all. That was the Japanese VSOP in the 1990s and the Russian Radio Astron in the 2010s. So there is a new mission, Millimetron, likewise a Russian mission with some international participation, which is currently under construction. So if that's ever going to happen as planned, okay, we cannot know yet. And there have been a few other proposals, like the BEX, the Black Hole Explorer, is currently maybe the most sophisticated one. So that then also, again, would put one antenna in an orbit around Earth and connect this antenna with antennas on the ground. Well, that's not what we're actually going to do, or what we are planning to do, because the problem is that then in the end you combine the disadvantages of both approaches. So, okay, one antenna is far away, so you get from Earth, so you get a much better angular resolution, but you still have antennas on the ground, so you're still limited by the atmosphere of Earth. So you cannot go to very high frequencies. In addition, Earth is rotating and the antenna is moving, so the sampling of the visibility planes, so this sampling function actually becomes, first of all, really complicated and usually really spotty. So, which means the image quality will be highly limited. So this is why we said, okay, so we need to get better than that. So we want to come up with a concept where we put several satellites in space and only use stations, VLBI stations in space to actually observe what we want to do. So we place several antennas in space. All of those antennas observe the same target at the same time, send the data to the ground, and construct in the data center. So we then construct, hopefully, the image of our target. So I mentioned before, so UV plane coverage is a critical issue, so especially for many ground-based observations. UV plane coverage with EHT data was always pretty spotty, for example. On the other hand, if you have several satellites in space. And well, what we did is essentially, so we say we have for Capella, Project Capella, we have 4 satellites in 2 perpendicular orbit planes. And in each plane, we have 2 circular orbits at slightly different altitude. So which means these 2 satellites move relative to, well, they both orbit Earth, of course, but both of them move relative to each other, so with maybe a few hundred meters per second. So which means sometimes they will be very close to each other, and sometimes they will be at opposite sides of the Earth. So which means you cover essentially all baseline distances, baseline lengths from a few kilometers, so up to more than the diameter of Earth. So in our case, so with our orbit configuration, about 14,000 kilometers. So essentially, so you get various kinds of, because it's now 2 planes of satellites, so you get basically overlaid spiral patterns, so that if you wait long enough, and in our case we say, okay, we need to wait about 3 days, taking into account shadowing by Earth and everything, in order to almost completely fill the UV planes within the maximum UV radius, so a UV plane radius, which is of course given by the maximum possible distance between 2 satellites. So this is actually an example for observing M87, which is famous for its supermassive black hole observed by the EHT. Then in this case, well, we can essentially paint down this pattern. So we assign in the UV plane, assign each point in the UV plane the value 1, and every other point which is not touched by the UV tracks, so the value 0. We take the Fourier transform of this, and we have the point spread functions of the observatory. And essentially, this is what we got. So we essentially we get a point spread function which is very symmetric, which is highly concentrated toward the center, which has a little bit of substructure, which is unavoidable. But especially by VLBI standards, I can tell you this is absolutely beautiful. And you have essentially, if you measure the width of the central concentration of this point spread function, so this gives you an angular resolution which is about 7 microarc seconds. So which is about a factor 3 better than the Event Horizon Telescope, and by a lot better than any other observatories we ever operated. Okay, so you can actually look at other targets like Sagittarius A star in the center of our Milky Way. The pattern here looks a little bit different because, well, shadowing by Earth is different depending on where on the sky is your target. So in this case, the UV plane coverage is a little bit more spotty, but nevertheless, so we get still by VLBI standards an absolutely beautiful as a point spread function. So which means once we're able to take an image, so with this or this UV plane coverage, so we will be able to clearly recognize what we are looking at. There has been actually one issue. Okay, let me be brief. There has been one issue, which is that, okay, Capella, the project, so the mission, the observatory, so is doable with existing technology. We know that. But on the other hand, space-to-space VLBI has never been done before. So we got a lot of requests from the community to also consider a simpler pathfinder mission, so not focused primarily on science, but focused on design, providing a convincing proof of concept, and helping with developing methods for data acquisition, data calibration, etc. And that's kind of what we came up with. So this is a project that we called Mimosa. Well, Mimosa is a bright binary star. So it's a system of two, it's a configuration of 2 satellites in slightly different circular orbits. Well, for simplicity, we assumed just one orbital plane. So because then basically you just need one launch from the ground to actually put both satellites in orbit or in their orbits. So at lower frequencies, so this is up to 100 gigahertz. So that's a frequency range where we can use simpler receivers, radio receivers, which are less complex to build and to keep cool, especially with a few other parameters, so that then are reasonable. And the interesting thing is, well, we only have one orbital plane, but if you have a target which is basically with a line of sight that is more or less perpendicular to this orbit plane. So you still get actually and wait long enough, so again about 3 days, so you get an absolute beautiful UV plane coverage, so like this. So we optimize this a little bit for observing M87, and well, this is actually what we get. So it's an absolute, it's a beautiful point spread function with an angular resolution because of a lower frequency of about 35 microarc seconds. Well, it's just one orbit plane, so it's a demonstration, the pathfinder mission. So once we're actually moving too far away, from the with a line of sight from the normal of this orbit plane, so then shadowing by Earth will get more and more severe. And well, observing another famous object, actually OJ287, which I briefly mentioned before. So we would end up with a more incomplete UV plane coverage and well, a more distorted point spread function. But well, nevertheless, it would be possible to at least see something here. So well, this kind of pathfinder missions would be the first step of what we then altogether call now the Capella program. So initially Capella was just the name of the science mission, the observatory, but including a pathfinder and verification steps. So essentially, we have a design where we could start with a pathfinder mission, the 2 mini satellites that make up the Mimosa constellation or the Mimosa interferometer. And then we could launch, so if we are convinced that everything works as intended, so we could start building and launching the 4 Capella satellites, maybe start with 2 first in a verification mission. And once they're in orbit and work as expected, only we would then launch the second pair of satellites, just in case there is some unexpected development so that we need to consider. Okay, now when it comes to designing this observatory, I mean, essentially we need to squeeze an entire radio observatory into a small satellite, into a few cubic meters. And how can we do that? So first of all, we know that 500 kilogram class satellites platforms are very common. So this is actually an example that's built in Korea, and they are essentially there are multiple commercial companies, providers around the world that could actually build this for you. For a VLBI satellites, so what we do need is we need a telescope to collect the light. We need a receiver to actually convert the incoming electromagnetic radiation to an electric signal. We need digitizers, samplers, and recorders to actually, well, digitize the signal and convert and make it to store the signal on board. And finally, we need to downlink it. We need to send it to the ground. Well, we need a frequency standard to stabilize the phase of the receiver, and to provide essentially a clock or a time standard, a time stamp, for the recording system. Well, for the stabilized sampler also, and to stabilize and to provide a timestamp for the recording system, and we need highly precise navigation, well, to know where our satellites are at any given time. And well, we need a common time frame. So like, for example, UTC, Universal Time. So that could be provided, for example, by the GPS constellation. So we need to build a very light, space qualified telescope. And well, we've done this before. So I mean, we've actually looked at in great detail at silicon carbide designs, because already 20 years ago, the Herschel telescope used actually a 3.5 meter aperture, a silicon carbide mirror. So if we scale this down to our needs for Capella and Mimosa, we would have a telescope mass of around about 70 kilograms. So for a Capella satellite, for a Capella telescope, and something like 13 kilograms. So then for a Mimosa satellite. And well, we are still exploring actually a few other options and materials, but we know that this can be done. So with the specifications, surface accuracy, so everything that we need, because it has been done before several times. We want to observe at a very high radio frequency, and essentially we need to use heterodyne receivers. So Heterodyne receivers means we need receivers that are able to preserve the incoming electromagnetic wave and to convert it into an electric signal with the same or with the corresponding amplitude, phase, and frequency. So we know how to do this because the ALMA observatory has 70 or had 70 of those such receivers built. So we know very well how to build such very high radio frequency receivers at low mass and in a very compact geometry. So exactly as we would need it for a space mission. Same actually for 100 gigahertz receivers. So for in case of Mimosa, we know how to build this kind of receivers. So we know this very well. We've done this for many years. We do need actually a very accurate, a very stable frequency standard. So this stability is then usually expressed in terms of the Allen deviation. So we have a certain parameter, we have a certain limit, so which says we need about, well, Allen deviation is essentially a normalized, so pairwise, measures a normalized pairwise fluctuation of consecutive data points. So we need an Allen deviation of less than or approximately equal 10 to minus 13. And it turns out, well, usually, so this is something that you would only achieve with atomic clocks, so especially hydrogen maser clocks, which, however, are very massive, so consume a lot of power, so they're not really the tool of choice for a space mission. Luckily, so a few years ago, so we have reached the breakthrough, so that small oven-controlled quartz crystal oscillators can actually achieve very similar specifications at much lower masses and power figures. So actually, so this box in the photo here on the left is currently on the way to Jupiter, so on board the ESA JUICE mission. So we know it can be done because it has been done before. Well, it's something we've been looking at also with some interest, but which we're not fully seriously considering yet, is that in the not too far future, so there may be the option to actually use a thorium-229 based nuclear clocks. So not atomic clocks, but nuclear clocks, because thorium-229 has a transition, a nuclear transition, which is actually at a few electron volts, so you can actually excite it. It turns out you can excite it with ultraviolet lasers and use this as a time reference, as a time standard. So essentially, you would have a device with the accuracy of an atomic clock, but essentially, since thorium-229 is a solid material, so in a crystal, so basically you could scale this down all the way to essentially the size of a smartphone eventually. But we are not that here. But in the last few years, the physics community has been very excited about that option. We need to actually to know the position of our antennas in space as good as possible. Ideally, better than the coherence length of the signal. Well, coherence length is essentially given by the inverse of the bandwidth, which is 4 gigahertz in our case. That's the coherence time multiplied by speed of light is the coherence length. So what we can do in our case is that we could actually split this band into sub-bands. For example, for one configuration, we looked at 16 times 256 megahertz, or you use 32 megahertz individual bands, so then the coherence length is a bit more than 1 meter. So this is an option so that we could use at the level of processing the data on the ground. So which means as long as we know the position of our satellites, or we know where they have been, better so then let's say something like 10 centimeters. So we can proceed with collating our data so in a relatively straightforward way. So actually, otherwise we might need actually multiple additional calibration steps, which may be very hard to do for a space observatory. Well, but we know how to do that because we've been doing this all the time. So this method is called precise orbit determination. And I mean, there are multiple examples of satellites that had their positions determined. Within 5 to 10 centimeters, so absolute accuracy. So we know how to do that. Last but not least, one thing we have to worry about is to sending the data to the ground. And luckily, so in the last few years, there have been important breakthroughs in optical communication. Okay, so what's the problem here? Let's say we have a signal with an electronic bandwidth of 4 gigahertz. So we want to sample the signal and digitize it and send this to the ground. So, okay, the Nyquist theorem says, okay, if you have a 4 gigahertz signal, you need 8 gigahertz sampling, so 8 billion data points per second in order to fully sample that signal. So each data point, of course, now requires a certain number of bits in order to be actually saved. And in VLBI, we use 2 bits per data point usually. So we lose a little bit due to quantization in this case, but it actually turns out it's a 12% effect, so it's okay. So okay, then we have 4 gigahertz times factor 2 for Nyquist sampling times factor 2, so for 2 bits per data point. So we have 16 gigabits per second, at which we generate data in each satellite. So data are stored on board, and whenever we have a common line of sight with the ground station, then it's the opportunity to send the data to the ground. But this, of course, requires, then ground stations are not always visible from the satellite. So this requires the data to be actually streamed to the ground, so much faster, than 16 gigabits per second, unless you would need substantial dead times in your observing operations. And luckily, with current systems, actually with some of them having been tested in orbit already, so this was the NASA T-Bird mission, for example, we know that streaming data from orbit, low Earth orbit to the ground by laser communication is possible at rates up to about 100 gigabits per second. Using near-infrared lasers, which are relatively insensitive to actual weather conditions, around the ground station. So, well, in case of polar orbits, we would need to place ground stations both at high northern and high southern latitudes if possible. For example, at existing polar research stations or satellite communication station, for example, on Spitsbergen in the high north. So this has been done before, but yes, of course, we would then actually set up the infrastructure on the ground to use Capella as intended. So, okay, taking everything together, we have been able to identify all the critical components, and it turns out, I'm not going into great detail here, but with existing technology, that's already available, so each of the key components that we need can be provided with the power and mass specifications that are suitable for a small class satellite missions. In case of Capella, the actual science mission, we would have a total power demand of around about 380 watts and something like 190 kilograms of payload mass. So which means the total satellite mass will be a bit more than twice that much. So around about 500 kilograms for the total satellite mass, and even somewhat lower numbers for Mimosa. So especially payload mass around 100 kilograms. So implies that the total satellite launch mass will be around 250 kilograms. These are small satellites which are relatively, by spaceflight standards, relatively inexpensive to build and to launch. Okay, so I've spent a lot of time already, and I'm not going to go into all the great details, but essentially I hope I could convince you that we have a plan, that we have, or at least we have a design. We don't have the money yet, but we have a design. For a space-based, a radio interferometer operating at very high frequencies that will be able to provide excellent images of sufficiently bright targets, so mostly AGN. At an angular resolution of around about 7 microarc seconds. And the important point is that then in the last few years, technology has evolved so rapidly that now actually is the time to do this. And now is the time that it can be done based on the technology which we already have. Okay, so that's all I wanted to bring up for today. So that was a lot of information already. So I think I stop here. And thanks for your attention. I'm happy to take questions.
Thank you, Sascha, for this really nice talk. Are there any questions? Yes, Jutta?
Yeah, it was a really nice, very interesting talk. I'm of course interested in when will we see something? Do you have some timeline, some idea? You say you don't yet have the money, but
Yeah.
possibly, yeah.
That's a very good question, actually. So in principle, so all the key technology already exists. Of course, we still need to actually make the final designs, make the final layout and actually build it. So, but once actually a space agency, or a major organization that can actually handle this kind of projects, supports it. So we could actually be in orbit within 7 to 8 years. So I would say.
Oh, that's great.
Yeah, so it's not a forever project. So
Yes,
because
yes.
this was actually one of the considerations we had, because I mean, of course, we could try to be more and more ambitious, or much more ambitious, but once you end up with kind of a JWST class to design, which takes 30 years to develop and build, and also billions of dollars or euros or other currencies of your choice, to pay for it. So then this is not going to happen. But this was actually kind of the one thing which surprised ourselves a little bit. So once we started to look into the details, it turns out, yes, the technology is there. So in principle, we could do it on a relatively short time scale.
Mhm. Yeah, that's great. And that you take 4 satellites, I mean, it
Mhm.
seems like this is some optimal number, right? And also astronomers don't want to kind of have too many satellites, even though
Yeah,
Musk puts
yeah, yeah, yeah,
plenty. Yeah.
yeah. Yes, actually. So we started for the science mission, so the actual Capella mission. So we concluded so that 4 satellites would be kind of the minimum that you need to actually achieve all your science. Simply because, I mean, when you're 4 satellites in two different planes, so then you always have a 3D configuration available. So which means you're always able to actually look anywhere in the sky where you want. Well, you will have some exclusion zones, which depend on the time and the season. There will be some shadowing by Earth because, well, you're going around Earth, of course. And of course, you cannot really point too close to the sun or toward Earth directly, or towards the moon. Which means you will have certain parts of the year. So there will only be certain parts of the sky you will be able to observe. But yes, if you have a configuration of at least 4 satellites, you are flexible, which means you can basically essentially point your observatory in any direction at any time. So if you like to.
Thank you very much.
Are there other questions? Maybe I can ask a short one. You
Go
said
ahead.
that the satellites will be roughly at 500 kilometer side. Is there a reason why you don't go further away? Because when I remember correctly, the larger the baseline, the higher the resolution you can achieve.
That's true. Yes. Essentially, yes. So we are also looking into somewhat larger distances. So the interesting thing is at those relatively low Earth orbits, so you have a few advantages which are a bit more tricky. So when you go farther away, so one advantage is you are still actually well within the magnetosphere of Earth. So you have a lot of natural protection from cosmic radiation, which is an issue. So when you are dealing with extremely sensitive electronics, so as we do in VLBI, so you kind of have to consider that. So you could shield your electronics accordingly, which would just make everything a little bit more massive and more bulkier. As long as you are well within the GPS or any other navigation satellite constellation, so you can use satellite navigation for precise orbit determination, so which is good. And essentially, of course, one thing that happens is, I mean, if you remember basically just Newton's law of gravitation, when you go farther away from Earth, so the orbital speed will be lower. So essentially, you simply would need more time for filling the UV plane. So that's of course a very interesting trade-off. So because okay, do you want better resolution or do you want better UV plane coverage? So that's a decision when you actually or whoever, hopefully someone at some point is going to sponsor this kind of mission. So that's a trade-off, of course, so we have to consider. So we could go farther outward, but then UV plane coverage might be either less complete, or so just might need more time per observation to achieve.
Thank you. Are there other questions? Okay, if not,
so I'm not sure if this means everything's clear, everything is unclear. But anyways, it was my pleasure to present our ideas here. And of course, I'm always happy to get contact by anyone who is so Torben, maybe you feel free to share my contact, my email address. So if anyone actually wants to know more about what happened. Well, I should say this is actually a bit just at the very bottom of this slide. So we do have a white paper. So the first version of this white paper was in the archive 3 years ago. So currently we are, I think that's archive version 5. So that's white paper version, I think 1.4 was the last version we have online now. So we keep updating it occasionally. So we are working on the specifications and keep working on it. Yeah.
So thank you again for the nice talk. Let me stop the recording.
Okay, then